he found that what is quite surprising, that when the ratio is very close to the 1.5, these two amplitudes are the same. And he analyzes different sources, and what was very surprising, that in many of them he found this behavior. Well, I should say that there is one exception, which is COX1, which doesn't show this. But all other sources, atoll sources mainly, show this behavior. So, of course, he showed to us, and Marek and Horak were convinced that it must be a signature of resonance. But at that time, we don't know how it goes with resonance together. So we developed a very simple model, which I will talk about. And this is the result of this model. We plot the same quantities here. On the horizontal axis, there is observed frequency ratio. And on the vertical axis, there is amplitude difference, of course, not in RMS, but in arbitrary units. And what we found is kind of oscillatory behavior, which is going on very short time scale, or short in comparison to time scale at which these power spectra are analyzed. And what we found, if you make some averaging over time, you will get something like this behavior. So it seems that it could be really some signature of the resonance, and that is motivational for this talk. So what is going on? This is the subject of this talk. And because we still don't know much about physics behind, we want it to be as general as possible. So we developed kind of semi-phenomenological model, and we know that there are two QPOs. So suppose that they are really harmonic oscillations, so they will be governed by two harmonic oscillators, and then we make some two harmonic oscillators are not models, so we must add something what will excite the resonance, or will produce the resonance. And we think that it's some nonlinearities on the right-hand side of these two equations, which couple them. And because it would be still too general to somehow solve it, or at least to discuss the behavior, then we impose one additional condition that is related to conservation of the energy, that we suppose that these two functions have such form that if you make time inversion, you will get the same. So, and we suppose that this coupling is very weak. That means that these two variables are small in comparison with unity, and then you can find that the solution can be expressed like just harmonic oscillator, which amplitudes and phases are slowly variable with time. And this time behavior is governed by very simple equations, which is quite surprising if you see how general we are still. So these two amplitudes are governed by these equations, and then there is this gamma, which is defined like this. You see that it's like something like phase difference, and this is governed by the third equation, which is like this. And of course, because we are general, the generality must be somewhere in these equations, and it is in these in the values of these parameters, beta, mu, and these two mu's. So any system described by these two coupled oscillators at the end are governed by these two equations, three equations. The difference between different systems are only in the values of these constants. And so it was first surprise for us that it's quite unique behavior. And of course for us, because we are considering the resonance, so two quantities are very important. Yes, please.
I'm just curious, you have a square of AL, AU, and then cube of AL, and then single power of AU. So there is a asymmetry between the two amplitudes.
Yes.
Where does it come from?
Well, it comes from, well, that's a good question. I think it comes from the resonance, because, well, I don't know.
Okay, you can answer that.
But, well, I should say that we suppose that, or we are, our additional assumption is that these two eigenfrequencies are close to utility ratio, right? And then you will see that, well, if I start to describe it, it could be 5 minutes. So I will.
So what happens with F on the previous?
What happens with F?
Yeah.
Well, what I did is Taylor expansion of this F. Taylor expansion. So you know that in Taylor expansion there are different coefficients of this expansion, and what is quite interesting that all these coefficients of the Taylor expansion combine here to these four constants only. Okay. Yeah, very good that you are asking. So well, so for us, two quantities are important: eigenfrequency ratio and ratio of observed frequency, which is given by this gamma dot, which you can see from here, because obviously it may be from here. That if you ask what is actual frequency of these oscillations, then of course it's this omega L, but of course plus derivative of this, obviously. So if you calculate derivative of this gamma, you will have exactly 2 times observed upper frequency minus 3 times observed lower frequency, and that is why it depends only on this gamma dot and not on the actual values of eigenfrequency. Yes, that's this. And of course, because we suppose that the energy is conserved, you can see that if I multiply this equation by lower A and this equation by upper A, then I will get on the right hand side, and perhaps I should multiply this equation by nu, that I will get on the right hand side the same term, so I can, or there is this minus, so I can sum them, and I will found that this quantity is conserved all the time, because its time derivative is 0. And therefore it's exactly this energy conservation which we supposed at the beginning. And you can, of course, then parameterize these two amplitudes by just a single variable, which is this psi, because energy is conserved, so you can do like this, and then you reduce the number of equations, so at the end we have only 2 equations, which looks like this. And what is quite interesting, you can find another integral of motion, so at the end you have only 1 equation, but I will not do it, because it's 2 equations is still quite good. And of course these 2 equations can have some critical points, which are given by zeros of these 2 derivatives. And well, and if you ask how the solutions of these equations looks like, you will find these figures. And well, at these figures, these are kind of polar plots, and the polar angle is this gamma, and the radius is psi. So psi goes from 0 to 1. If psi is 0, then all energy is in the first mode. If psi is 1, all energy is in the other mode. and gamma just goes around. And and then what is also important is ratio of these two and energy. So you can find that depending on values of these two quantities, which are constant all the time, you can find three different kind of topologies of this plane. And for example, this critical point exists only when energy and eigenfrequency ratio are in these regions. Okay, so this is example of this trajectory, and this is example of this, and this is example of this. There are these two critical points, and in this region only one critical point. And critical points are quite important because you see that they are solutions of this system, and therefore gamma dot is equal 0. And therefore, if your system is in this critical point, it means that because psi is also constant, so the two amplitudes of the modes are constant, and more or less the frequencies of the oscillations are in exact 3:2 ratio. Then if you are following these trajectories, you see that gamma is always increasing or decreasing, and well, I think in this case increasing, and it means that the ratio of these two oscillations which you observe, of the frequencies of these two oscillations, will be always greater than 3:2. And if you go in the opposite sense, which is the case in this region, ratio of these two oscillations, ratio of frequencies of these two oscillations will be always less than 3:2. And of course, if you're following some trajectory from this region, then at some point gamma dot is equal 0, and the ratio of the frequencies of these two oscillations is oscillating below and above the 3:2. This is quite interesting behavior, and of course, well, when one wants to see something, one always finds some of that, or well, with some kindness of the audience, you can see that this is behavior which may be really observed in the true systems. And here I show you the observation of SCOX1, which is very bright source, and therefore people are able to do this careful analysis. And what they found is that, so these are power spectra, that the system is oscillating between these two states, and the frequency of these oscillations is 6 Hz. So we have two peaks. Here is not very obvious, but we have two peaks at different frequencies, which are very high. And these two frequencies and amplitudes of these two peaks are modulated on the frequency which are very low, which is this 6 Hz. So we have low frequency modulations of high frequency signal. And what is quite interesting, that it is exactly what we predict just by this very simple model. So then let us ask what happens if the system is not stable all the time, or not in the same state all the time, but the parameters of the system are slowly changing. Obviously, one must consider this effect in the case of neutron stars, where you see that these two frequencies of these two peaks are changing over the very long range. Therefore, obviously, eigenfrequencies of these two oscillations must change in the time, and therefore the ratio will change in the time. And of course, if you want to have something more concrete in mind, you can imagine this torus, which is moving slightly inward, and therefore eigenfrequencies of all modes are slowly changing. And so I need only the ratio of these eigenfrequencies is slow function of time. It means that characteristic time of these changes is much longer than any time scale, so which I spoke about so far. And therefore, what will happen is that the position of your position in this graph is slowly changing, and when I am changing eigenfrequency ratio, I am going across this resonance tone, and therefore the topology of these planes are changing. And what we suppose that really happens is that therefore your system is at the beginning following one of these trajectory, which is given by initial condition, and then the topology is slowly changing in time. Therefore your system is changing from one trajectory to another trajectory very slowly.
I'm sorry, but perhaps on the other side, for this side of the room.
Oh, sorry. Yes. And but when you came to this resonant tone, then topology will change, and then this region will appear. And it may happen that if you are following, for example, this trajectory all the time, you jump to another trajectory in this region, and you are following this trajectory. But because the topology is still changing, it happens that you escape from this region after some time on the other side, and therefore you will end with, suppose that we are following this trajectory, then I enter to this region, so I am following this trajectory. And because everything is changing, I, after some time, escape from this region, and I am following this trajectory. I will show you some results, and maybe it will be better understood. Okay, few results. So this is one example. I've put these parameters for the system, and I must fix somehow the energy of the oscillations, and I am changing slowly the ratio of eigenfrequencies from this value to this value, and it takes this very long time. So the system is at the beginning following this trajectory. As I am approaching the resonance, this trajectory is more and more non-circular. Then I enter to this Arnold, so I'm going this way. Then I enter to this resonance tone, and so I change the sense of orbiting, and then I escape from this, and I end with different trajectory. And if I plot the observed quantities like frequency ratio and amplitude difference, I will get this behavior.
Can you clarify what the amplitude, what amplitude difference here? Depends on your A.
Yes, it's lower minus upper amplitude.
So AU minus AL?
Yes, AL minus AU.
Oh.
Which is this psi times P minus 1 minus psi times. So this was one example. The other example, what could happen is that the system is trapped in this region of vibrating trajectories for a longer time. So I'm starting with this. Then I enter to this region of vibrating trajectory. So I'm doing this, and then I escape from this, and I end with this trajectory. So you see that obviously because I'm longer time in this region, there are many times in which the frequencies the observed frequencies are in 3:2 ratio. And if I plot how observed frequency ratio depends on eigenfrequency ratio, I will get this. I start with somehow a monotonic behavior, or at the longer time scale. Then I am trapped in the resonance for some time, and then I escape from the resonance and continue. So again, if one can look at the real system, whether we really observe something in this, like this in QPOs, and this is even more gentle than before, so one really must be very kind to see it. But we have this, so on the horizontal axis there is lower frequency of the QPO, and on the vertical axis there is the upper frequency of the upper QPO. And we see that there is some kind of monotonic trend, which some people fit by linear functions, some other people fit by power law. But, well, it seems that as the system go across this 3:2, that kind of these frequencies are trapped or are more closer to this 3:2 line. But well, it's a question for observers what they would say about it. Yes, and here I'm just showing how it depends on initial conditions. So these are many solutions of these equations. I think the parameters are the same as here. So I am changing the eigenfrequency ratio from this value to that value over this time. But I'm changing, I'm starting with different initial condition. And for each initial condition, which is given by initial psi, which is on this horizontal axis, I get different value of the final psi after I cross the resonance. Do you see that there are these two classes of solutions? One is connecting to this to the first type of solution, and the other one is with this resonance trapping of the system, which is connected to this. What is quite interesting is that this qualitative behavior is not very sensitive to other parameters like initial phase, for example, or even the velocity with which I cross the resonance. Okay, so that's everything. Here are some conclusions. We can conclude that these amplitude changes close to some rational ratio could be good signature, or is natural signature of the resonance. Well, in this jump, the observed frequencies are in exact 3:2 ratio, and then there are some issues which should be answered in future. For example, all these observations are done for RMS amplitude, but of course we have some physical systems, so we have physical amplitude, and it's not obvious that RMS amplitude and physical amplitude are the same, or at least they are proportional in the same way in both modes. So for example, it's the question mainly for Michal, who is doing this this modulation. So I don't know. So that's the question of modulation mechanism. Of course, one should discuss what happens if I have non-conservative system. So, for example, I have some damping. It seems that's very important. Will still be such feature, and then of course one should take some more concrete equations, not such general, but to have some good specific model. But I think that these equations were so general that maybe even your model could have something like this. The only thing what we need is that these two modes should be somehow coupled non-linearly. Which
Then here we go. 5 minutes for questions.
So, could you clarify how you did this? How do you actually tune or change the frequency ratio? Because I thought that the way you would do it is by having a small d over dt term, a small change in energy. But it sounds from what you're saying now that you actually have conserved energy and you tweak something else in the system.
yes,
You change the frequencies by n.
yes, exactly, by hand.
But how do you? So can you? If you go to the equations.
Well, I'm changing these two.
Okay, but so you have a. I'm trying to listen what that corresponds to in the equations.
Sorry.
You're integrating in time.
Yeah.
So you have some numerical scheme where you solve the first equation you had. Let's do the first one you showed us. The first slide. Oh, the second slide. So these are the equations you integrate?
Actually, these.
Oh, you okay with this one?
Well, I don't know whether I still understand what you want to say, but
I'm just trying to understand
I
what
think I
exactly did you
understood
solve
what you
on the
asked.
computer numerically, and how do you change the frequency in this equation that you solved?
I think I understood your question, and there is a very trivial answer to it. You have a phenomenon, which is these oscillations, which are described by these two harmonic oscillator equations, which Irka showed us at the very beginning. Okay, and there is a characteristic time scale for behavior of these oscillations, which is, say, inversely proportional to these eigenfrequencies. And there is another process which goes on a much longer time scale, and therefore we may change these eigenfrequencies by hand. It is like we always do. For example, stellar, we are solving static cases in stellar evolution, and then there is a very long time scale behavior. So that is consistent.
There are various ways of doing it, I guess.
Well, but then you may, if you like, you may say that it's a sequence of kind of a stationary
model.
model.
It's not a formal time integration.
okay.
I thought that you were doing a formal time integration of the original equations. The first equation you have is a second time derivative, so you could go forward and integrate this, but it's not what
okay. So you are asking how I get from
you
here.
integrate that on the computer with us.
I see to here. No.
No, he's asking in the d gamma by dt equation, do you just put in omega u as a function of time and omega l as a function of time with some long time scale variation?
Yes, but well.
So does that conserve energy would be your question now?
Well, that's a very good question, of course.
Adiabatic approximation.
But
yes,
slow change in energy changing on a much longer time scale.
Yes, but there must be some slow change in energy of the system. I was trying to understand.